Ladies and gentlemen, welcome to the Teijin Aramid webinar. Thank you very much for joining us today. First, I would like to introduce the speakers. My colleague, Christian Böttger, is the Global Technology and Application Director. Christian has more than 30 years of experience in ballistics. My name is Nicolas van Zijl. I'm in charge of sales in EMEA, that's to say Europe, Middle East and Africa, and both of us are working for the Safety and Life Protection platform. We will be your hosts for today's webinar. How does mechanical stress impact the ballistic performance of body armor? That's a question we will discuss today. Before doing so, I will give a brief overview of Teijin Aramid, and Twaron. Afterwards, Christian will take over and discuss the technical part, the methods he used, and also the results discovered. We will share then the results on Twaron and on ultra-high molecular weight polyethylene. At the end, we will have a question and answer session. And here, we would like to have your participation. You have on the right side of the screen a functionality which allows you to send in your comments, but also your questions. And these questions, we will try to answer them at the end of the session. So your participation is most welcome. So let's give you a brief overview of what Teijin and Teijin Aramid is. Teijin Limited is a technology-driven Japanese group listed on the Tokyo Stock Exchange. It's more than 100 years old. More than 20,000 employees, generated a revenue of about $8 billion in the last fiscal year. And Teijin Limited is focusing on two areas. The first one is healthcare, and the second one is materials. Materials being resins, composites, plastics, fibers. When we talk about fibers, it's polyester, carbon, and different aramids. And this leads to Teijin Aramid, a 100% subsidiary based and headquartered in the Netherlands. Teijin Aramid has 1,800 employees working from 8 sales offices worldwide. We have 6 production facilities in Europe and in Asia, and 5 R&D facilities globally. Teijin Aramid is focusing on 4 main markets. Safety and life protection, you heard about that before, automotive, industrial, and aerospace. We have a portfolio of 4 different high-performance products. Technora, it's a para-aramid, and Technora is produced in Japan. Then we have Teijin Konex, which is a meta-aramid fiber produced in Japan and in Thailand. And Teijin Konex is used in flame and fire-resistant applications. For instance, military pilot coveralls, tank crew garments, police anti-riot suits, but also for firefighter garments and so on. Then the third product is Endumax, an ultra-high molecular weight polyethylene used in ballistic applications. And then Twaron is a para-aramid fiber, which is produced in the Netherlands from monomer to filament, which is quite unique. And Twaron has been commercially available as of 1986. And then the production capacity has been increased. And now, while we are speaking, we are increasing the capacity by another 25%. Twaron is really proud to be number 1. Over the last 3 decades, Twaron has proven its reliable performance in soft and hard ballistic applications. It has a combination of unique properties, and I'm talking here about a few. It is extremely strong. If you compare Twaron with steel, for instance, at the same weight, at equal weight, Twaron is 5 times stronger than steel. Twaron has a very good, stable performance over many, many, many years. And it is very resistant against heat, cut, and most chemicals. This combination of these properties makes Twaron an ideal material for body armor. It's this lightweight and this high flexibility which gives the wearer, such as police officers, soldiers, a lot of mobility and a lot of comfort. And if you put all together the lightweight, the flexibility, and the stable performance, you have the key criteria which create a lot of acceptance as the wearer. That's to say, the police officers, the soldiers wear their body armor. And we all know, only body armor which is warm can protect. After this short overview, I would like to give now the platform to Christian, who will cover the technical part. Christian, the floor is yours.
Thank you very much, Nicola, and hello, everybody. I will first start giving you an overview about the test methods we at Teijin apply and the analysis tools we use in order to judge the ballistic performance of materials, but also to judge the safety margin of ballistic constructions. Just a second. Okay, here we are. Most of you have already heard about terms like such as V50, for example. For those who haven't, V50 is the velocity at which the probability for a complete perforation of a projectile impacting a ballistic construction is 50%. So this we consider an ideal measure to judge the pack-specific energy absorption. And it allows us to compare the ballistic capability of different materials against each other. Some people would also use V50 as a value to judge the safety margin of a ballistic construction, but that's not what we do. That's not what we consider appropriate. So for safety margin of a ballistic construction, we consider the V05 to be the better value. And the V05 is the velocity at which the probability for a complete perforation, so that the impacting bullet would perforate the armor, is only 5%. And in order to have a good safety margin, or at least a sensible safety margin, we suggest that, and this is in line with what is written in the NIJ standard, that the V05 should be higher than the VREF max. And the VREF max is the velocity that is specified in the test standard. So as an example, the German police standard requires a 9mm bullet to be shot at 415 meters per second. Then there's a plus tolerance of 10 meters per second. So the V415 is the reference velocity, and the 425 would be the VREF max. So in order to have a sensible safety margin, your V05 should be higher than the 425 meters per second. So with this, we conclude that the V05 is a better indicator for the safety margin than it is V50. In order to follow the presentation, there are a few other terms I need to explain to you, terms which I'm going to use. And that is the VLCP, which is the velocity at which, the lowest velocity at which full perforation occurred. Then there is a VHPP, System is a bit slow. The VHPP is the velocity at which the highest partial perforation occurred. Anna, if you can hear me, I have difficulties to navigate. So, now it comes. So the VHPP is the velocity at which the highest velocity at which a bullet has been stopped by the armor. And then there is a zone of mixed results that is called a ZMR, which is the difference between the highest stop shot and the lowest complete perforation. In order to better understand, I'd like to illustrate this to you in a graph. So here on the x-axis, you see the velocity of the impacting projectiles. And on the y-axis, you have the perforation probability. And then the solid red line is your reference velocity. So in case of German police, 415 meters per second. And the dashed line is your VREF max. So that's a 415 plus the tolerance of 10 meters. So the maximum velocity required by the standard. So if you now do a ballistic test, you only have two possible outcomes. Either the bullet is stopped or the bullet is perforated. So if you do multiple shots at different velocities, then you would have a lot of bullets that are actually stopped by the armor, which are dotted on the blue. Each blue dot here is one single shot, and the stop shots are all dotted on the 0 line, and all the perforated projectiles are dotted on the 1 line. And so you see, in this example, shots were done from 410 to about 530 meters per second. And you also see that your highest stop shot has been around 495 meters per second, and your lowest complete perforation has been about 435. The difference between the two now is your zone of mixed result. And what we now can do is, by applying a well-known statistical analysis tool, which is called Logistic Regression, we can plot such an S-curve. So this logistic regression is very suitable for such situations, and is also the system that is specified in the NRJ standard. And from such an S-curve, you can derive different information. The slope of this curve depends on the width of the zone of mixed results. So the wider the zone of mixed results, the more flat your S-curve is. The quality of the S-curve, that depends on the number of shots you are doing. So the more shots, the better is your confidence of this S-curve. Let's look into another example. In this case, we have yellow data points. So it all looks very similar. However, if you look at the zone of mixed results, you see that it is much smaller in this case. And as a consequence of that, the S-curve is much steeper. So what kind of information can you derive from that? You can, for example, look at the V50, which is the velocity at which the perforation probability is about 50%. And if you compare the two armors here, you would conclude that both armors are identical and they have the same performance because V50 is identical. However, due to the S-curve, you can also look in the V05. And there you see, while comparing the two armors, that there's a dramatic difference. So in case of the blue example, the V05 is slightly below the VREF max, so you don't have enough safety margin. In case of the yellow example, however, the V05 is more in the range of 450 meters per second, so substantially above the maximum reference velocity. So looking at the V05, you can see that the yellow example has a higher safety margin and is the better product for the person wearing the vest. Having all this in mind, we started to investigate and analyze the wear resistance or the resistance against mechanical stress of different ballistic materials. And for this, we use the NRJ conditioning protocol, which asks to do a tumbling trial, Tumbler test. So how does that look like? The Tumbler test is basically a kind of drum dryer where ballistic panels, a specified number of ballistic panels, are filled in this drum dryer. The panels are, at least in our case, and I think that is standard, the panels are heat sealed in a pouch, and then they are additionally stitched in an outer garment in order to protect them as much as possible. The panels are rotated in this drum dryer for 10 days, which is equivalent to 72,000 rotations. And the conditions are 65° centigrade and 80% relative humidity during those 10 days. So during the rotation, a lot of mechanical stress is applied, and this is how such a panel, in this case it had been removed from the outer garment already, how such a panel looks like after the 10 days of tumbling. So you can see a lot of wrinkling, folding, mechanical stress has been introduced to the pack. What can happen, not necessarily does happen, but what can happen to the material, to the panel, due to this mechanical stress? So this is a typical S-curve for a material prior to tumbling. So you see a relatively steep S-curve and a small zone of mixed results. What we see from time to time is that this zone of mixed results substantially grows because you happen to have lower velocity complete perforations over here. So due to that, the zone of mixed results grows. And if that is the case, then your S-curve after tumbling, which is now the dashed curve, substantially flattens, which means that your V50 and your V05 substantially reduce. Not saying this has to happen, but this is what can happen due to the mechanical stress that is applied. Which materials did we actually investigate? Which materials did we test according to this procedure, this tumbling procedure? It was a Twaron woven fabric called CT612. In this case, we choose for loom state fabric. We compared it with Twaron UD called UD25. And we included two types of ultra-high molecular weight polyethylene UD we obtained from the market. Both are based on generation 3 ultra-high molecular weight polyethylene fiber. Tumbling was done, as mentioned, in accordance with the NRJ 010106 standard. The ballistic test we did is an internal test method we described within Teijin Aramid. The projectile used in this test is a 9mm DM41, which is a steel-jacketed 9mm round as specified by the German police, where the reference velocity is 415 meters per second and the VREF max is 425. The analysis method we applied is logistic regression, as specified in the NRJ standard. And in order to come to a good quality result, we tested each construction with 80 shots. So for that, we used 10 panels, and each panel was shot 8 times. So based on our statistical analysis, we are convinced that this gives us a good estimate on the V50 and also on V05 with acceptable confidence levels. Some extra information on the panel constructions. So the CT612 loom state, which is a 125-gram plain woven Twaron fabric, was put in a 4.5 kilograms per square meter panel and has been quilted. The Twaron UD25 is a 2-ply UD with 112 grams, was put into a 4.24 kilogram per square meter panel and has been corner tacked. And both of the ultra-high molecular weight polyethylene materials we used were 2-ply materials put into about 3.9 kilograms per square meter construction and also were corner tacked. So you see some difference in the panel construction. While the Twaron panel, the woven fabric has been quilted, the UDs have been tacked. And this is because those are the most common ways to connect the layers when an integrator, vest manufacturer is producing a vest. So for woven fabrics, especially for loom state fabrics, it is very common to have them quilted. While for UDs, quilting is not common at all because it would dramatically stiffen up the pack to often to an unacceptable level, and the quilting would also have some impact on the ballistic performance. So the ways of the panels, the panel constructions we used are typical to what is used in the industry. Prior to tumbling, all the panels were heat sealed in pouch and garment. Before entered into the tumbler. And once removed from the tumbler, the garment and the pouch have been removed again. The panels were flattened out in order to have them as straight as possible. So how do the different materials look like before and after tumbling? Two examples. Here we have a comparison of the woven Twaron panel, new versus conditioned, so after tumbling, and you see that due to the tumbling, there's quite some stress provided to the panel, which you can see especially in the corner area, but you also see that the fabric construction is very well intact. And here is an example of one of the ultra-high molecular weight polyethylene UDs, where you can see that due to tumbling, a lot of stress, a lot of wrinkling and folding is introduced to the UD, and in some the fiber or the UD construction starts to deteriorate. After the testing and after reconditioning the samples under norm climate for some time, we executed a ballistic test. So we compared the ballistic performance of the different materials before and after tumbling. So here you see the V50 of the unconditioned and here the V50 of the conditioned materials. So what you recognize is that in case of the woven Twaron, the V50 did not change at all. In case of the Twaron UD, we saw a minimal drop in the range of about 4.5%. And in case of the two ultra-high molecular weight polyethylene materials we tested, we saw a drop in V50 in the range of 10 to almost 13%. Same analysis we did for the V05. So you remember the velocity where the probability for perforation is 5%. Again, in the case of Twaron woven fabric, you see that the ballistic performance did not change at all, no impact due to tumbling. In case of the Twaron UD, a somewhat more pronounced drop in the range of close to 9%. And in the case of the two ultra-high molecular weight polyethylene UD materials, we saw a drop in V05 between 20 and 33%. And even more so, also the safety margin was substantially reduced even below the reference velocity. You remember the reference velocity was 425 and the constructions we used, which are not certified solutions, but the constructions we used had a V05 substantially above and suddenly they are substantially below the VREF max. Looking at the graph again, this is the S-curve for one of the UD samples before tumbling. And this is the same material after tumbling. So you see that the curve substantially flattened, meaning the V50 and the V05 substantially reduced. And in comparison, the woven Twaron panel has a steeper S-curve prior to testing. And more importantly, the dashed line now, you can hardly see it because it is so close to the original line. The dashed line is exactly on top of the untumbled, unconditioned material. So the V50 and the V05 have not changed at all. And with that, I would like to hand over to you, Nikolai, again. Thank you for your attention.
Thank you, Christian, for this detailed explanation. Summarizing the results of this comprehensive program, we can conclude that wearers need reliable body armor. That's to say, soldiers, police officers need body armor which still performs when heavily worn. This comprehensive test demonstrates that ballistic materials made from Twaron enable a stable performance even after extensive mechanical stress. So well-designed Twaron body armor provides the confidence wearers, but also procurement officers are looking for. So Twaron is a material of choice for reliable, comfortable body armor. This concludes now this part of the webinar, and we are now going to start the question and answer session. I am looking at the chat box, which we have here on the right side, and where you still can send in your comments or questions. And I'm now asking the first question to you, Christian. You are talking about mechanical stress. However, the tumbling process involves heat and moisture as well. That's what you also mentioned in the presentation. Could these factors have a higher impact on the performance than the mechanical stress?
That's a very valid question, and I can very well imagine. I mean, we don't know for sure, but we can assume that the elevated temperature and the moisture that is provided to the panel supports the stress that is applied in the mechanical during the tumbling. So we don't consider this a hydrolysis test, because for hydrolysis resistance, to measure and analyze hydrolysis resistance, 10 days would for sure not be sufficient. So that is why we consider it a mechanical stress test. However, indeed, and it also depends on the type of material, because in UDs you also have resin systems, for example, which might be affected, for example, by the elevated temperature. So indeed, the moisture and the temperature applied will further support and increase the stress.
Okay, thank you. Another one here, why do you consider the Tumbler test a relevant test?
Yeah, first of all, we apply the test because it is requested in one of the most important test standards globally, which is the NRJ standard. But looking into the NRJ and following the presentations NRJ has been given on the standard, on the Tumbler test, we learned that it has been developed after the Cylon case we had in the United States several years ago. And NRJ was able to demonstrate that with this Tumbler test, the behavior of Cylon in actual use could be simulated. So based on that learning, we conclude that the Tumbler test, even so it's not a test from which you can predict the lifetime of a vest, nevertheless, we believe that the Tumbler test is a good test to simulate somehow the stress a vest would see in real life.
Okay, good, thank you. Another one here, why did Twaron UD degrade more than Twaron fabric and less than PU UDs, so polyethylene UDs, sorry. Can you explain, please?
At least I can try, and I don't think I will have a full answer to that question. It's of course a question we ask ourselves as well. First of all, of course, we have differences in the panel construction, so that might explain at least partly why the woven Twaron behaves different than the Twaron UD. Also, you have resin systems on the UDs, which is not the case with the woven fabric. So the resin system could explain the difference between woven and UD, and partly also the panel construction, but it would not explain the difference between ultra-high molecular weight polyethylene and Twaron. And I cannot answer the question yet why, in case of ultra-high molecular weight polyethylene, we have seen a more pronounced drop.
Okay. I have here another one. If I understand well, the tested panels were not made up the same way. Why not? And can that have, as these are two parts, why not? And can that have an influence on the test results?
Yeah, that goes a little bit in line with the previous question. As I explained during the presentation, we specifically choose for different panel makes-up because we wanted to use panel constructions that are typically used in the market. And while for bullet-resistant vests, it is very typical to quilt woven fabrics, it is not typical to quilt UD materials because that would result in very, very stiff constructions. And due to the lamination of the UDs, the impact of needles stitching through the material would be higher. So the stitching of UD would influence and negatively affect the ballistic performance, which is much less the case for woven fabrics, where the yarns and the filaments can still more easily move and be pushed aside. So that was regarding the first part of the question. The second part, indeed, it is well possible that this difference in panel construction partly influences also the performance after tumbling. But as I already said, the Twaron UD as well as the ultra-high molecular weight polyethylene UDs have been, the packs made from those have been produced in the same way, and still we see a substantial difference in performance after tumbling. Okay,
good. Thank you, Christian. By the way, can you look at the camera because I don't see a picture anymore, but because I have still one more.
Yeah, I don't know, but the camera obviously had switched off.
Okay, good. But I have still one more question, and I would like you to reply to that. Even you did quite some testing, V05 is just a mathematical value. How relevant is it?
It's a mathematical value as V50 as well, coming from the logistic regression. So it's due to the logistic regression, you calculate a graph, you calculate the function, and the S-curve you see in the pictures is just a visualization of that function. So basically, for each you can derive every single value, V50 or probability, perforation probability versus velocity from that graph. So we consider it a very relevant value coming from that function.
Okay, good. Christian, thank you very much. We don't have any more questions at the moment. Nevertheless, I would like to thank, first of all, the questions we have got, your active participation. Second, we recognize that it was quite a tough presentation, a lot of technicalities. Therefore, if you would like to get in contact either with Christian or with me, you have here the contact data. Don't hesitate to come to us. We will try to help you. This webinar has been recorded and will be made available for you. So you can then, in your leisure time, have another view on it and to listen to it again. And I think that was it. I would say thank you very much to all of you for listening, for participating, and We wish you all the best. Have a nice day. Goodbye.